All right, do you remember back in chapter 2? We were solving things like y double prime plus ay prime plus by equals 0. And we had a whole bunch of theorems that said things like, how many solutions do you need to find? Two. Why do you need to find 2 solutions? Because it's a second order equation. But you don't need to find any 2 solutions. You need to have, the 2 solutions had to be something special. They had to be not linearly dependent or linearly independent. So we had a big theorem that said, if you have 2 linearly independent solutions, then any other solution can be written as y equals C1 times your first solution plus C2 times your second solution. That was our big theorem in the beginning of chapter 2. In order to solve a second order homogeneous equation, you needed to come up with 2 linearly independent solutions. And once you had the 2 solutions, you really had them all. What we have in chapter 5 is all the same theorems. The difference is, in chapter 5, we have let x1, x2, xn be n solutions of a homogeneous linear system. Why are these x's in bold font? They're vectors. Okay? So x1 might be something like e to the 2t times 3 negative 5, or something along those lines. It would be a vector solution. But what it says is, if you have solutions, you can multiply by constants and then add them all up, and you still get another solution. That's the exact same theorem we had back in chapter 2, except our solutions were not vector solutions, our solutions were just functions. But we said if you had solutions, you can multiply by constants, add them up, and you still have a solution. Then, the next thing we had in chapter 2, we talked about something called a Wronskian. Suppose x1, x2, xn are n solutions of the homogeneous linear equation x prime equals p of tx on an open interval. Let w be the Wronskian of x1, x2, and xn. If the vectors are linearly dependent, then the Wronskian will be 0. And if they are linearly independent, the Wronskian will be not 0. Liam.
Will we be getting this handout, or is this?
Got a pile of them right here for you.
It's got to be right in bold on
It is. That's why when I draw vectors, I draw them with a little arrow like that. All right, so here's the big theorem. The big theorem says, if you have n linearly independent solutions of a homogeneous equation, then you have them all. So it's the exact same theorem that we had back in chapter 2, except our solutions are now vectors, not just functions. So if you have a 3 by 3 system of equations, how many answers do you need to come up with? 3. You need 3 vector solutions. Once you have 3 linearly independent vector solutions, you have all the solutions. And then finally, what if you have a non-homogeneous system? Then what do you need to find? Well, in chapter 2, when we had non-homogeneous solutions, what did we have to do? You have to find the particular and you have to find the complementary, and then you add them together. Same thing works with non-homogeneous systems. To solve a non-homogeneous system, you have to find the particular solution, you have to find the linearly independent complementary solutions, and then you add them all together. Liam.
So in that example where you have the vector equal to either 2t and then the matrix 3, -5, what does that actually mean? Is that saying that you have 3 e to the 2t minus 5 e to the 2t, or what was that saying?
All right, so this makes a lot more sense with an example. So this is number 22 out of your book. You have, your equation is x prime is -3, 2, -3, 4 times x. What's x? Yeah, so what we really have here is the vector x has your two variables x1 and x2. So the vector x prime is x1 prime, x2 prime. So what I really have here is x1 prime, x2 prime equals -3, 2, -3, 4 times the vector x1, x2. But over here on the right-hand side, how do you multiply two matrices? You go across and down. So this is just a fancy way of writing the system of equations. x1 prime equals -3x1 plus 2x2. And the second equation, I go across and down. I'm going to have x2 prime equals -3x1 plus 4x2. So what we'll be doing in this, in the next section in particular, we'll start with a system of equations that looks like this. We'll write it in this matrix form, and then we're going to learn an interesting technique for solving systems of equations in that matrix form.
And we'll start on with solving with just one variable, and then we'll look at two variables.
Well, it's a system of equations, so it's got to have at least two variables. So it's got to have an x1 and an x2. We could use x and y if we wanted to also. The book tends to use x1 and x2. But you could call this one x and this one y. That would work. Okay, then what it does, the book says, here's two solutions. So solution number one, it claims, is the vector e to the 3t, 3e to the 3t, which could be written as 1, 3 times e to the 3t. So that's what a solution is going to look like. There's one solution. And then vector x2, the other solution, it says, is 2e to the -2t and e to the -2t, which could be written as 2, 1 e to the -2t. Okay, so the book asks us to do two things. First, it asks us to show, three things actually. First, it asks us to show that these really are solutions. Then it asks us to show that they are linearly independent. And so then, once we have two solutions and we know they're linearly independent, what do we have? We have all the solutions. Okay, so first off, how are we going to show that this really is a solution of the equation? Plug it in. So by plugging it in, that means I have to take the derivative and then multiply by this matrix. So what's the derivative of 1, 3 e to the 3t?
3.
It would be 3, 9 e to the 3t equals negative 3, 2, negative 3, 4 times 1, 3 e to the 3t. Are those really equal? Well, we just have to multiply our matrices on the right-hand side and check. We have 3, 9 e to the 3t equals negative 3 times 1 plus 2 times 3. 3, because it's negative 3 plus 6. And then we have negative 3 times 1, which is negative 3. 4 times 3 is 12. Negative 3 plus 12? 9 e to the 3t. Those are equal. So that first one is a solution. Do you believe that the second one's a solution?
Yes.
Yeah, okay. We believe that. Good. I won't work through that then. Okay, now, how do I prove that these two things are linearly independent? I got to create the Wronskian. So what's the Wronskian for these two solutions?
3, 9, and 1, 3.
I need these, and I need the e's. So what we're going to do is we're going to take the first answer, and it's easier to write it in this form. E to the 3t, 3e to the 3t. And then we take the second solution, 2e to the negative 2t, e to the negative 2t, like so. So you just take each solution, you take the first one, you put it there, you take the second one, you put it there. And then what do you have to do with this Wronskian thing? You cross multiply to find the determinant. So I multiply this way. What's e to the 3t times e to the negative 2t? E to the t. Minus, I multiply the other way. That was 3e to the 2t times 2e to the negative 2t. 6e to the t. That's negative 5e to the t, which is not 0. So are those linearly independent? Yes, they are linearly independent because the Wronskian was not 0. Finally, the general solution to this equation would be x equals what would it be? We would have C1 times e to the 3t, 3e to the 3t, plus C2 times 2e to the negative 2t, e to the negative 2t. Questions on that?
Basically just verifying.
At this point, we're verifying that they are solutions. We're not actually finding the solutions, correct?
So I can understand like what we're doing, but what does the matrix actually represent? Like what does that matrix of e to the 3t and 3e to the 3t mean? Like are they solutions to a separate equation?
So what this really means is I could rewrite this as, normally in section 5.2 we were writing answers this way. I could write it as x1 would be the top row. So x1 is c1 e to the 3t plus 2c2 e to the negative 2t. And x2 is c1, 3c1 e to the 3t plus c2 e to the negative 2t. So that's what these say exactly the same thing.
So the x2 could be y.
Yeah, if this started off as x and y originally, then this would be x equals y equals. Yep.
Thank you.
So the general idea is, what we're going to see in section 5.4 tomorrow, is we start with a system of equations. We start with two equations with two variables. We convert it to a matrix equation, which is now one equation with one variable. The only variable is x. And we will learn a technique to solve a matrix differential equation. So that's the idea. We're turning two equations, two unknowns, into one equation. And the exact same technique would work if you had three equations with three unknowns. You could take three equations with three unknowns, convert it to one equation, and then solve the one equation. Okay? So that's kind of the goal. That's where we're going. Questions on that?